we go. Got our little introductory going. Welcome to our Honest Investigators Talk Shop show, where we talk about the reciprocal system of physical theory by Dewey B. Larson at the LRC Physics website also, and here on our LRC Physics channel of YouTube. So we're really happy to welcome you. Today is Saturday, January 23rd, 2016. And we're going to be talking about a multidimensional scalar number system that subtitled Scalar Mathematics for Scalar Motion and Scalar Motion for Scalar Physics. It's lecture 3, part 3. If you go back and watch the other parts of this lecture, you'll see some of the more basic information that you may be curious about, but of course we can't cover that on each show. So we're going to skip the introductions, except to say that for Dewey Larson's theory, we have to make the disclaimer, because this is his system of theory, but he developed his theory under the what we call the reciprocal system of physical theory, RST, as on the basis of rotation of scalar vibrations, and we don't think that really follows, and so we've taken a different tact here to develop a system that is strictly made of three-dimensional motion with two reciprocal aspects, space and time, and in discrete units. So anyway, we've talked about that, as I said before. So what we'd like to do, we'll have a Skype, well, if we can get it to work, session after the presentation, but what we want to do right now is see if we can bring up our slides and take it from there if it works. Hopefully it will. Okay, that looks pretty good. We also have a little marker system here that I'd like to also bring up. Oh, okay, excuse me here, I'm trying to bring that up and I didn't do it right. Okay, where is it? Maybe it's behind here. There it is. Okay. So now we will be able to make markers if we need to emphasize certain things. So a multidimensional scalar number system. Now, as I said, this is the third part. Today we want to see how magnitudes, dimensions, and directions are really part of both physical magnitudes and numbers. And our number system is a little deceptive in its notation, because it doesn't always, let me adjust the sound here a little bit. It doesn't always appear what it's really saying. But if we look, as we did last week, at the tectactris, the binary expansion in the tectactris, we can see plainly that the 2 of the binary is has to do with the two directions, in quotes. We put it in quotes because it really has to do with polarity, positive and negative polarities, rather than directions in the sense of a compass direction. But the 2 then stands for directions. Oh, gee, I'm sorry. I go talking and it looks pretty good to me. I didn't actually pull it up. Okay, now there it is. So you can see what I'm talking about. So we have this 2 directions here. Oops, I thought that was on highlight. And that has to do with the fact that there are two directions or polarities, plus and minus, in each dimension. Of course, when you go up in the dimensions, then those multiply. So as this goes from 1 to 2, for instance, the number of directions goes from 2 to 4. And when dimensions go up to 3, then we've got 8 directions. And then in between that, though, is this multiplier of units. Normally it's 1, so it's not shown. But we can see that over here there's a magnitude that, you know, really wiped out the Pythagorean cult many years ago, many centuries ago, because they had a lot of cultic theories on numbers. But this number here wasn't really a number. It was a physical magnitude. They knew how to calculate it, but it wasn't a number. Square root of 2 was not a whole number. And so that threw things off. But what we're trying to say here is that the magnitude in one dimension, in a scalar sense, goes out in two opposite directions in 1 unit of time. So when you expand this out from a point, you go in both directions in one-dimensional directions. If you go, I couldn't show it all here, but if you go in 2 dimensions, then that would be 4. You'd have 4 diagonals in a square from the point expanding out in 1 unit of time. And then in a cube, you would get what we call Larson's cube, a 2 by 2 by 2 stack of 1 unit squares, not squares, cubes. So anyway, we've explained that in more detail. This is just kind of a review. We've explained it last week, and so I urge you to go back and see what that was in last week's, how we explained that in last week's program. All right, but the next slide has to do with the fact that within the 2n cubed progression, so when n is 1, we have 2 to the third, which is 8. And then when n goes to 2, we go to 64. And 3 takes us to 216. And 4 takes us to 512, and so on. This is a progression that goes on ad infinitum. And it's according to the 2 directions. And the magnitude n here is 1, and then changes to 2. But we can see that within that cubic expansion, 8, 64, 216, 512, and so on, we can define 3 volumes of continuous magnitudes. One would have the square root of 1, which is, of course, what we just writing it in a different sense, because that's equal to 1. But a 1D progression then is 2 times this unit of square root of 1 to the third power is equal to the square root of 64, which is, of course, 8. So that's the one we know. But there are these other 2, the red here and the blue depicted, where the red is the square root of 2. So if we substitute that unit into the progression series, where n now becomes 1 times the square root of 2, and then 2 times the square root of 2 when it doubles, and so on, then where we begin then is the square root of 512. So 2 times the square root of 2 is the square root of 8 cubed would give us the square root of 512. So that's with this unit when n is equal to this unit. And when in the 3D case, it's equal, because in that cube, you know, you have those 8 diagonals going out to the 4 top corners of the stack of 8 unit cubes, and then, of course, 4 more going down to the bottom 4 corners. So you have that each one of those expanding out in the proper direction. So in the 1D case, that would be 2. In the 2D case, that would be 4. And in the 3D case, that would be 8. But it's times this unit, not 1, 2, 3, 4, you know, n equal to 1, 2, 3, 4, but n equal to 1 times the square root of 3, 2 times the square root of 3, and so on. So at 1 times the square root of 3 cubed, we get the square root of 1,728. So we've tried to depict that. You see here, these are not in scale, of course. The red ones would be bigger than the black, and the blue ones would be bigger than both of them. But you can't show everything graphically. It's difficult. But here, the radius you see is the square root of 1, and then 2 times the square root of 1, and then 3 times the square root of 1, and then 4 times the square root of 1. Each time they go out in the number of directions that that it's expanding in. And normally that's just, we think of n here as, if it is 1 or the square root of 1, we normally just write that progression as 8, 64, 216, and 512. But at the same time, we have these other diagonals that are expanding. So in the two-dimensional case, that diagonal is the square root of 2. So we go square root of 2, 2 times the square root of 2, 3, and 4 times the square root of 2, which gives us these numbers here. So then, of course, the same thing in terms of the square root of 3 for the three-dimensional case. And so we have all three of these going on in that progression that we normally think of as 2n to the third. All right, well, let's move on to the next slide. How come I'm not moving on here? There it is. Now, this is interesting because we can study. Now, see, I've kind of drawn these in scale. I mean, it's not perfect to scale, of course, but at least it gives us some idea that the inner ball of the LRC, not the LRC, the LC, the Larson's cube, when it's 8 or 2 by 2 by 2, a stack of 8 1-unit cubes, then it fits right inside there, and its radius is equal to 1 or square root of 1. But when we move to the two-dimensional, that just fits around the two-dimensional slice of that cube, and with a radius of square root of 2, then it's, of course, a little bigger, and n is equal to the square root of 2 cubed, and so that gives us 512 and 1728, as we saw in the other. Now, what's really interesting is that we can write the middle volume in terms of start at the one-dimensional level. The one dimension of the middle ball, the red one here, is actually equal to the black one. It's one-dimensional diameter, I guess we could think of it, times the square root of 2. And then to get the two-dimensional, would be a circle, a slice of the ball, we would simply multiply by the square root of 4. And then to get this three-dimensional version, we take the three-dimensional of the inner ball to multiply it by the cube of 2, square root of the cube of 2, and lo and behold, we get the 3 dimensions of this. So we got 1, 2, and 3 dimensions in here. And then to do the blue, we get the 1, 2, and 3 dimensions of the outer ball by multiplying the inner ball by first the one-dimension component by the square root of 3, and then the square root of 3 squared, and then the square root of 3 cubed will give us the volume. Multiply the square root of 27 times this, and you get 1728. So square root of 64, or 8, times the square root of 27 gives us the square root of 1728. Now, that is really interesting because it shows that we have a relationship in here that might help us analyze what is happening in our motion combinations, and that's really important. So here I've rewritten this so that we understand this could have been all black. Well, it is all black, but this could have been all red, and this could have been all blue to match. But if we have 8 directions when n is equal to 1, square root of 1, for instance, some multiple of the square root of 1, then we get these values, 2, 4, and 8. But when we substitute the multiples of square root of 2 in square root of 2, then those 8 directions are times that unit, so we get the square root of 8, and then the square root of 64, and the square root of 512, and so on. And in the blue ball, we have that same relationship. So, and there's a relationship between these, so that this, of course, you can see is the square of the 1, and then this is the cube of the one-dimensional when we have n equal to the square root of 3. Now, when we add these, we can come up with 14 values. We have 14 directions, but when you try to add the square roots, it doesn't work. I don't know exactly why. It comes out to irrational numbers, but that may be telling us something in and of itself, but we need to research that a little more. But this is an amazing discovery that, you know, it makes sense, but it may not, we may be going down the wrong road, we don't know. But it's our sense of a three-dimensional scalar number system. And so it, like we said in the last week's lecture, there are 3 scalar numbers in here, with a unit of scalar 1, a unit of scalar 2, and this is a mistake. That should, when I say scalars, square root of 1, square root of 2, and this should be square root of 3. That was a mistake there. But we can put it in a new number system. And it's our normal number system. When we do 1 over 1, 1 minus 1 is 0, 1 minus 2 is minus 1, and so on. 2 minus 1 is 1. So you can see this is a normal group of integers or rational numbers from which everything that we use is based on. And then, of course, we add I, and we put this in a vertical sense, and we have discussed the problems that come from that. But we're thinking in terms of three-dimensional units. So this is really a three-dimensional unit. The black unit here, or the inner ball over another inner ball, and so on. And you get the same thing. You can't tell that the number is a three-dimensional number. But then when we use the square root of 2, we can do the same thing, and square root of 3, same thing. So we get the exact same thing, copies, even though we substitute the unit number. And so again, that's really amazing. It's all composite. As the LC expands, all of these numbers are contained in that 2n to the third progression. We just have to make the proper substitutes. Again, over here, each one has its one-dimensional number of directions, that's 2, two-dimensional number of directions, that's 4, and three-dimensional number of three-dimensional directions, which is 8. Each one has that. So it's a little bit difficult to depict it all in a simple fashion, but hopefully you can understand what we're talking about here. All right, well, now these combinations can be calculated this way, and we can say, well, we got these oscillating balls inside here. Somebody's going to take issue with that, I'm sure. But the fact is if it has any physical meaning, we have to prove that. But we can at least see that they're in there, and we can calculate the various components, scalar components that are associated with each one. And we know that our ST units, now remember, again, I keep referring back to last week's program, but you'll understand that S stands for Suter, which is a space unit displacement ratio of space and time, and T stands for Tutor, time unit displacement ratio. but we don't like those words, so we use S and T. And we'll see here in a minute how those can be combined. But each ST unit, we might have one number of S's and another number of T's, any combination, like a balance. Think of it as a teeter-totter. You know, we can have somebody with twice the weight of one person, of the person on the other end, or vice versa, and so on. So this is like where one is the middle, 1 over 1 is middle, and then we can have 1 over 2 or 2 over 1, as we saw in the number line there. So we know then that this corresponds to our number lines, but there's 3 number lines in there. That's the thing. Well, anyway, when we do that, and we have a combo, it has a net volume. In this case, what's 1 S and 1 T, so that's a net volume of 0. We, of course, use 1 over 1 because that's 1 unit of space for one unit of time, which is the speed of light. But when you subtract the 2, then it's 0. So it depends on whether you're going to use a fixed coordinate system as your reference, or if you're going to use the rational numbers as the reference. We use the rational numbers because space and time is a rational number. So anyway, you've got a vibration of space, and you got a 3D vibration of space and a 3D vibration of time, and it has a net volume. And it consists of then the ratio of 3 independent S subvolumes, and then on the other side, on the T side, 3 independent T subvolumes. That's what we're saying. It's a little bizarre, a little different, but we're going down that road. All subvolumes, V sub I, the inner one that fits inside the stack, and then Vm, which fits around the 2 dimensions of the stack, and then V sub 0, which fits around the 3-dimensional stack, or whether the stack, fits inside it. So you get the square root of 3 as its radius, and for Vm you get the square root of 2, and for Vi you get the square root of 1. But they all oscillate synchronously. Now that's very interesting and should have some implications further down the road. But one thing that we need to understand is that one cycle of oscillation, this volume oscillation, if you'd call it, or oscillation of these 3 balls, is equivalent to 4 pi rotation, or 720 degrees rotation, which puzzles the LST community because they know they have to use a quantum spin that is equal to 4 pi, but they know that it can't be spin, number one, in the sense of something rotating, but they have no other way of representing it. So they represent it with a asterisk saying that it's really not possible. But we see that quantum, so-called quantum spin, when it's a 3D oscillation, a volume oscillating, how easy it is to understand it. Because what you have, we begin with a point, and then in what's equivalent to 90 degrees of rotation, we get this amount of volume, an eighth of amount of the volume, and then at 180 degrees, or 2 pi over 2, which is pi, we get a 1/2 of the expansion, and then 3/4, and then this should be a little bigger. It's not quite showing there, but at this point is completely full when the equivalent of 360 degrees of rotation have occurred. And then we go back the other way to collapse, because this is only the half cycle from one point to fully expanded. Now in the second half of the cycle, the contraction, we go, and this is represented here as starting from this point here, and another 90 degrees rotation takes us down an eighth, and then 180 degrees takes us down, and so on and so on and so on. I should say a fourth, not an eighth. The whole thing is an eighth, but so this would go for 1/4 and 1/2 half, and 3/4, and then finally back to our starting point. So we have 2 pi rotation, a rotation equivalent of 360 degrees. And then the second half of the cycle is another 2 pi, or equivalent to another 2 pi of rotation, another 260-degree rotation. So 4 pi rotation, or 720 degrees, is required to return to the starting point. Voila, quantum spin explained so easily. Well, you can see that now in our natural progression, where we have 2 units of space let's say space and time oscillation. You can't do both at the same time, but if we represent the oscillation by the advance of time by 1 unit here, at the same time the reversal, or the collapse as we're calling it, takes place, then you can see the resultant vector is to 0 here, and then this vector, as time continues to expand in this red arrow here, and space is equally expanding, then the resultant vector takes us to, and this should be thought of as 3-dimensional, takes us to the full expansion. So contraction, expansion. Now, if that didn't happen from this point, there was no reversal, the time would continue progressing like this, and then again on the second half, it would continue to progress, and space would do the same thing. So that would put us out here, see? So we got 2/2 at this point. 2 units of space for 2 units of time. And that's really of course, that's equal to 1/1 as well, but that's when you start trying to figure this stuff out, you realize that's the basic oscillation, or that's the basic unit of progression. Is 2 units of time over 2 units of space gives us, takes us to this point, which is unity. And that I should have maybe put in a text box there that said 2/2. So we would have 2, we need a black color probably. All right, so again, this would be 2 units of space over 2 units of time, which is of course equal to 1/1. Then this would be, here would be 2 more, so this would be 4/4, and so on, 6/6, as we progress in this unit, what we call unit progression, P. Okay, so that's our natural frame of reference. It's our natural progression. It is a change of space of 1 unit over a change of time. And so when we do that, if there's an oscillation, that changes the space-time ratio up our number line. So now we have 2 units of space for every unit of time, because time's oscillating. And over here, it's just the opposite. We have 1 unit of space over 2 units of time, because space is oscillating. So there's one down, or one contraction, and one oscillation over 1 unit of space. So you see how that follows the number line of rational numbers. So as we go on in the space progression, then as the oscillation occurs, there would be 2/1, and then 4/2, and 6/3 in the case when this is oscillating. And when time is this is when time is oscillating here, and so you see the black arrow here. Actually, time is increasing in this axis, and then space is oscillating, reversing, as you see each time. Okay, and then over here, time is actually reversing direction, and that produces our oscillation, 3D oscillation of the volume. So anyway, I hope that makes sense, but it's important to understand that this now gives us something to work with in combining units of scalar motion. So when it's 2 over 2, 4 over 4, and it's going up that diagonal of unit progression here, instead of black, it's colored violet because it's a combination of the blue progression of space and the red progression of time. So the space unit displacement ratio progresses in time. The time unit displacement ratio progresses in space. This is amazing. So we can write this as a formula where we have the equivalent of the tutor, the suitor, the space unit displacement ratio that is oscillating and producing this rational number because it's oscillating in space and progressing in time. And then the tutor, on the other hand, is progressing in in space and oscillating in time. The denominator C is S over T is the denominator is 1 because it goes out once and then back one. Well, we have to also add this term because there's 2 of these actually, but so we have to account for it. So this would be like a contraction and this would be an expansion. And same thing here. This would be an expansion of space, and then this would be the reversal contraction of space. So to count the actual motions involved, we have to add this third term. Then we add the denominators, the numerators, and the denominators, and we get a total, a minimum total for the ST unit of 1 suitor and 1 tutor, 1 S unit and 1 T unit of 4 over 4. Now we can see that this is equal to 0 here if we use the coordinate system because 1 minus 1 is equal to 0. All right, so that's going along this violet line and magenta or whatever they call it, I don't know. But let's say then that's going along here as a photon. This is what we've identified as a photon. If you go back, we explain a little more in detail in our past programs. But here, a suitor now is coming along, progressing in time, and bingo, collides with that one. So now we're assuming that it combines. And so now we have 2 S's to 1 T. So that cocks us off a little bit. Now, exactly how much we have to calculate, but we don't know. But you can see that it goes to something less. It goes to the space-time, the suitor point of thing, where there's just the straight up and down is just pure progression in time and no progression in space. And so it changes our formula. Here we have now 2 of these. No. This one is the S unit. So we have 2 S's, each is 1 over 2. So that gives us 2 over 4. And then that increases our middle term because now we have 2 units going in and 2 units going out. But the T side of the ratio has not changed. There's still the 1 and 1 of the time, the 2 over 2 is reduced to 2 over 1 by the oscillation. But when you add the numerators, you get 6. And when you add the denominators, you get 6. So we can see that we're balanced. But here we have a minus 2. It's on the minus side and this side of progression. And then over here, we have the 1 side right here in the middle term. And so minus 2 plus 1 is a minus 1 for this guy. Now over here, it's just the opposite. We have a minus 1 right here and a plus 2 in time. So you combine those two and you get a positive 1, which means over the speed of light right here in the violet. That's violet. I guess that's magenta. Purple, anyway. All right, so you see that's off into the faster than unit velocity side of things. Okay, well, so then we can refer to our schematic representation that you've seen before in the last presentation. We explained a lot of it. We have in there these ST combinations, and we have a way of representing whether the combination is balanced or not. If it's balanced with n number of S's and in the same number n of T's, then it's colored green. But if there are more S's than T's, then it's colored red. And if there are more T's than S's, it's colored blue. All right. So when we can combine these for photons and bosons and so on, and you have to go back to our last lecture to kind of see how that works. But our point here is what we want to see is how the formula changes now when in this configuration we get 3 of the 2s to 1t st. So this one here in the middle, we take 3 of those and join them in a triangular configuration, and lo and behold, we get the electron with a -1 charge. And it's made up of these 3 units of unbalanced motion, unbalanced to the space side, which is negative. And so each one of them then, if you recall, was instead of 1/2, it's 2 of those, 2/4, which gives it the unbalance to the red side. The blue remains at 2/1, which is the minimum. So that gives us this equation, and now we multiply it by 3 because we have 3 legs here. And so 3 times 2 is 6, and 3 times 4 is 12. And notice it's a unit here that we're changing. So n is changing. That's the important thing to understand. And so 3 times 2 is 6 here. 3 times 1 is 3. 3 times 2 is 6 here. And 3 times 1 is 3. And so they all add up. 2 and 2 and 2 is 6. And 4 and 1 is 5. And another one is 6. So that gives us this formula here, and that is equal to a -6 and a +3, which is equal to a -3. And so this has a -3 charge, which exactly matches or complements, we should say, the proton's charge of +3 based on the same mathematics, the same reasoning, see? And then for the positron, we do just the exact opposite, and we get a -3 and a +6, which gives us a net of +3. So this one have +3, this one would have a -3, and it turns out that that's the antiparticle of the electron. Anti is, and it makes a lot of sense because this is space displacement, as we call it, to the left side of the number line, and this is the above unit speed, above the speed of light on the time side. So it's there's a lot of things that we could say about it, but they'd be premature right now. We just want to get this idea of how these work here in terms of our normal number line. 1/1, and you add, that is the unit value, and 1 unit removed to the positive side is 2/1, and 1 unit removed to the negative side is 1/2. And that's how we normally use it. But now we have these 3 radii. The one, which is derived from the Pythagorean theorem, where we have one of the terms of a three-dimensional formula populated, the other two are 0, and then we populate two of them when n is equal to 1, and that gives us the square root of 2. And then if we populate all three of them, let's see, I keep forgetting to delete those. When we get all three of them populated, that gives us square root of 3, which is this radius here for the outer volume. And then the red is the inner volume, square root of 2, defined by the two-dimensional slice of the three-dimensional stack of 1 unit cubes. And then, of course, inside that stack, the unit is 1, or the square root of 1. So we have a 2D slice here now, if you can see it, of the three balls. And the black is the volume of the inner ball. The red is the volume of the middle ball. Did I say inner? The black is the volume of the inner ball. The red is the volume of the middle ball. And the blue is the volume of the outer ball based on their radius, based on the radii here that we've derived. Now, of course, you have to include the constant, appropriate constant of pi in there. We have 4 pi divided by 3 to get the actual volume that would be multiplied by cubing this radius, and the same thing with the others. So what we have here is terms of these three sets of dimensional components. Just like the stack of cubes, the three balls that are contained in the LC contain three sets of one-dimensional, two-dimensional, and three-dimensional scalar components. And those are all contained in the combination of units depending on what n is. So when we add and subtract and multiply and divide by these LC units, Larson cube units, we are actually changing n here. And that's what makes all the difference. So volume 1, 1D, is equal to 2 times the square root of 1. And we saw that example moving out in two opposite directions, positive and negative, in one dimension. But in two dimensions, we have 4 directions. So we'd have from the center point out to this diagonal, and then this one out. I didn't draw the bottom line there, but then this one would be the second one to that diagonal to that corner, and this diagonal to this corner. Oh, I clicked on it, darn it. Let me get the thing here. So anyway, this would be, I can't draw very well. There would be 4, right, to each diagonal, and then I can't show the three-dimensional one because it's too hard. This is a two-dimensional slice, but it's actually equal to the square root of 3 here. So within each volume, though, we have a one-dimensional line, a two-dimensional area, and a three-dimensional area. And so we multiply the number of directions times the unit. And the unit changes for each dimension. So this is a little misleading. This should say volume 1, VI to the first power. I thought I changed it. I must have lost it somehow. And VI to the second, and VI to the cube. And then we get the directions times the appropriate unit, and that gives us the answers that we saw before. But that is repeated in each of the circles, each of the volumes. Each of the balls has a black black dimension with 2 directions, and a red that's supposed to be red. This really fouls me up. I can't say this because these are misleading. This, like I said, should be Vm to the 1, Vm to the 2, and Vm to the 3 instead of what it says here. And I swore I changed that, but I must have not saved it or something. But anyway, I hope that makes sense. We have 14 directions in each ball, the black ball, the red ball, and the blue ball. That's what it amounts to. But each one, see, there's another mistake. This should be 1 here, not the square root of 1, not the square root of 2. So anyway, I hope that makes sense. We have these 3 scalar components, 3 dimensions in each ball. All right, now, as we then take that information and take a 2s to 1t st, that is 1/3 of the part of the electron. Here then we have n is equal to 2 on the red side, but n is equal to 1 on the blue side. So here, let's take the blue side first. We have 2 directions with square root of 1 in each direction. Here we have, I didn't change that either. Doggone it. I changed them, but I didn't save them, I guess, and I closed it without saving them. So there's 4 times that square unit of 2 unit, and then we have 8, as I've explained several times now. And so many of these should be the same. So 4 and then 8, and then 2, 4, and 8. Okay, and I've got them correctly listed over here. But this is when n is equal to 1. 1 times the square root of 1, 1 times the square root of 2, 1 times the square root of 3, and so on. And this, again, should be square root of 1. And so on down the line. But over here now, n is equal to 2. So the unit, the multiple of the unit has changed. We have, not only do we have two units like we should, 2 directions, I mean, like we should. Oh, you can't read that. But 2 directions here is the same as 2 directions here in the one-dimensional case. But now we have 2 of the square root of 1. And here, when we have 4 directions, we have 2 of the square root of 2. And here, when we have 8, we have 2 of the units that are square root of 3. So, and that's the same all the way along. Again, here's this mistake. That should be 1. All right, so I hope you can see that. That really is important and will enable us then to see, given the relations between these 1, 2, and 3-dimensional components, will give us lots of room to work. Because remember, and I should have it here, but I don't, but S over, now this is not S pipe T, but S divided by T is equal to velocity. And the inverse of that, T over 1 unit of space, is the dimension of energy. And then if we take the dimension of energy and square it, then we get the dimension of momentum. And then if we cube it, we get the dimension of mass. And so if we multiply the dimension of mass, T is equal to energy if we multiply it by the square of the speed of light. So energy, T over S, is equal to T, it's hard with a mouse, cubed over S cubed, the dimensions of mass, times T square, velocity squared. So that would be S, this is supposed to be an X here, S squared over T squared. And so there you have it. That's Einstein's famous equation, E is equal to mc squared. So this is important. We can't do that. Here's the point. We can't do that if we don't have a multidimensional scalar motion. I mean, a scalar number system. We only had unit 1 that we normally use, and we're not going to use I because we're not doing rotation. Imaginary square unit, square root of -1 is I. And so if we square I, then we get -1 and all that we've explained. If you haven't seen that before, you can go back to our previous lessons, but discussion. But then we can't use that, right? We have to have this, and it turns out that what we have to have is there. Of course, the proof will be in the pudding that it makes, and so we'll be talking about that next time. Now, if you have any questions, you can Skype us, and during this lifetime of Saturday the 23rd, it's now almost 8 o'clock. We did have some live viewers, but they're gone now. But hopefully at some point we can get people either to join us on the Hangout here, where we would have their picture down below, and they can make comments and join in the discussion, or we can have people who don't want to do that but can Skype in with questions or comments. So hopefully we can do some of those kinds of things as we go forward. But for now, I think that's the sum of what we wanted to present in terms of the multidimensional scalar number system that we can use to find our electrical, which are 1D phenomena, and our magnetic characteristics of these particles that were identified as the standard model, and also the mass characteristics of it by using this multidimensional scalar number system. So hopefully that made sense, and I think we'll leave it at that. But I'm sure, I wish there were questions. You can also submit questions if you have them at the comment below. And I also would like to remind you that you can like our channel and you can subscribe to it, and you can also visit our website and our Facebook group. If you just request to join, we can make sure that you're part of that, and then we can discuss things in that forum as well. So anyway, that does it for tonight, and I hope everybody has a good evening, and we'll see you next week here on Honest Investigators Talk Shop Show.